Good afternoon. Yesterday we have seen one problem where, like I section, where shear stresses we have already found various locations, different 3 locations. Yesterday we have done all the calculations, but the only graph or the plot which we are going to do the distribution of shear stresses was remaining. So today I will just write those, I will draw that section, I will write those values which we have found yesterday, and we'll see how it varies. Okay. So first, I section. This was I section which we have done. We have found stress at this location, here 2 locations. This is neutral axis, also similarly here and here. Okay. I will write those values. At outer fiber, stress is 0. Then we have 2 values of stress. This is 1.57, also 19. Okay, one other value will be 19. And at neutral axis, we have stress value as 26.4. 26.4. So these are various values which we have got yesterday. And it is parabolic distribution. Okay. So parallelly, I'll draw this. Okay. These are salient points. So it is 0 here. Then we have 1.57. Okay. Then again at same location we have 19. So 1.57. Then we have 19. At neutral axis we have 26.4. So it will be like this. Okay. Till here it is symmetric. Obviously 26.4 Newton per mm square. This is the shear stress distribution across the I section or across the depth of the I section. You can clearly see here. Initially at the top fiber it is 0, then it is 1.57, that is bottom of the flange, that is what we have seen yesterday. Then also at the top of the web it is 19, at the neutral axis it is 26.4, which is maximum shear stress which is acting onto the neutral axis. Then again it is a symmetry, so mirror image you can draw. Here also it is 19, here it is 1.57, and here again it will be 0 megapascal. So this is the actual shear stress distribution for the I section. Okay. So the problem which we have done previously, where we have found bending stress, at that already you know areas, you know bending stress, maximum bending stress. Okay. And suppose if force is also mentioned to you, then you can draw the shear stress distribution, because in exam there is most likely chance that you may get a question where both the things, where like bending stress calculations also you need to do, and similarly shear stress calculation and graphically represent them. Suppose if both these things are asked, then that type of problem you can expect it around for 14 to 16 marks. So methodology is almost same. You need to find y bar. So in case of bending stress also you need to find the y bar. Then we need to find the moment shear. Okay. Then find bending stress in case of bending thing, and in case of shear stress distribution, find the shear stress at various locations, and ultimately draw the distribution of bending as well as the shear stress. So you can try for I section, T section, then you can have rectangular section, you can have any. So we'll stop here for that first part, deflection equation and shear stress thing. Now, sorry, bending equation and shear stress. Now today we'll see deflection. Okay, what is deflection in beams? What is general deflection equation which will be used in finding the deflections? Okay, so write down deflection in beams or beam deflection. Deflection in beams or beam deflection. Here, whatever design of beams which we have seen or which we have done till now, onto the strength criteria. Means what? We check for beam not to fail for its loads. If I am analyzing one square cross section beam and I just check it with strength criteria by keeping the view that it should not fail under stress criteria, I will check its allowable strength and I will check, suppose if it is less than allowable strength, the beam is safe. That is what I can conclude. But that is not the only thing which I need to check. Sometimes under various types of loads, beams tend to deform or deflect. Okay, they will deflect, and that deflection is nothing but sometimes their deflection will go beyond certain degree. So that deflection also I need to keep it in a control or keep it in a check. If beam deflecting more, then I need to check rigidity criteria also, where permissible deflection may be in case of degrees or with respect to the movement, vertical distance traveled, that will be given to you, and I need to check with respect to the slope also as well as deflection. So when I am checking with the other criteria, that is rigidity criteria, and also I am verifying with the strength criteria, then you can, like, it is a perspective, like both the like beam design can be verified by both the things. That is, sometimes some designer may be interested in limiting deflection of a beam, that he may not allow beam to deflect beyond some limit. At that time, your design approach should be based on the deflection equation, and simultaneously you should also check for strength criteria. Okay, but various, like based on the application, beam deflection is also most important parameter. So first we'll see what is deflection means. 2-3 definitions we'll take. We'll see just introduction, and then we can derive general deflection equation, which is with respect to the examination perspective as well as your learning. Okay, write down introduction. The selection of the beam based on strength criteria, the selection of a beam based on strength criteria where maximum bending stress did not exceed the corresponding allowable stress. So initially what we are given, the selection of a beam based on the strength criteria is done. Okay. Then, however, in most of the cases, it is also required to consider rigidity criteria, where maximum beam deflection should not exceed limiting value. Okay. Means what? Based on strength criteria, we design on allowable strength, and in case of rigidity criteria, deflection limit will be given. If beam extends that deflection limit, then we consider that it is a... Okay. Next, write down. Deflection. Definition of deflection we'll see. Deflection. It is a distance through which a point on a longitudinal axis displaces in a direction transverse to the longitudinal axis. Okay. So here we'll see. I'll draw one simply supported beam, and which is subjected to some point load. So generally, this beam will deflect like this, or this beam will bend like this. Okay, it is simply supported at two ends. You can call this as A end, you can call this as B, and this will be your C. Now, this distance, whatever it is there, is called beam deflection. That is Y. That is what we have given. It is a distance through which, at a point on a longitudinal axis, displaces in a direction transverse to the longitudinal axis. So this is longitudinal axis. This is the point. Under this load, this point, this location I have taken as the maximum location. Okay, you can see here some deflection is there, here some deflection is there, here some deflection is there. So it varies. Okay, deflection is maximum at the where load is acting. That is what we have considered here. There is only point load. So this is any point you can consider. Suppose if this point it has displaced on next point. So this distance is nothing but the deflection. Similarly, here I have considered the center point which has displaced the maximum. So this vertical this distance is nothing but the Y. Nothing but the deflection. Okay. Next, slope. Slope at a point is the angle between tangent to the deflection curve at that point and axis parallel to the longitudinal axis. Okay, so tangent. So this is the deflection curve we call, or beam deflection. This is how it has deflected. So next, what will we do is, I will draw one tangent to this deflection curve. Okay, I'll consider this maximum point. I will draw one tangent to this deflection curve. Right? Then again, this is the longitudinal axis. I will draw one parallel line to the longitudinal axis. So this thing, whatever it is there, is nothing but the slope. Suppose if this is your deflection curve, draw one tangent, you take this will be your theta. That is nothing but the slope of the beam. Okay? Tangent to the deflection curve. So, sorry, at that point little bit, we'll see one more time. You can see it here clearly. This is simply supported beam subjected to point load. So it may go like this. So tangent and one parallel. So this is nothing but your angle between tangent and parallel line with respect to the longitudinal axis. That is nothing but your slope. Okay. So these two things are important for us because we need to get the deflection is nothing but the point on a beam, how much it has displaced, and slope the tangential angle the point and a longitudinal. These two things you need to know because we'll be now deriving generalized deflection equation. We'll get one deflection equation by double integration method, and that will be useful for you. And what we have is cantilever beam subjected to point load, and also UDL subjected to point load. So these two case studies we have. One I will be doing, that is cantilever subjected to point load, and simply supported beam subjected to point load. Just you revise, you just check. Methodology is similar. Then there are numericals onto this. Okay. So first we'll derive deflection equation, which is most important thing. Okay, from this part. So write down derivation of deflection equation. Derivation of deflection equation. Derivation of deflection equation. Consider a cantilever beam subjected to point load at its free end as shown. At its free end as shown. Due to application of load, the neutral axis is bent into curve. The neutral axis is bent into curve. Okay. So first draw one cantilever beam. Cantilever beam is a beam where one end will be fixed and other end will be free. It is subjected to point load W. It is shown like this. Okay. Then due to point load or due to this load, what will happen is this beam will bend into such portion. It will be like this. Initially beam is straight. When we apply load, beam will bend like this. Okay. On this, what I will do is I will consider small portion that I will name as a DL, which is at a distance of X from fixed end. So initial condition is this. This is application of load. That beam has bent into one curvature. Similarly, its neutral axis will also bend into curve. Okay. This end is fixed. So you can take down. Draw one cantilever beam subject to point load and its curve. It is bent into one curve. Okay. Now write down. Deflection along the length of the cantilever. Deflection along the length of the cantilever can be written as deflection is equal to y, which is function of x. Means what? It is a y. Y is a variable. What is variable? Variable is nothing but the deflection, which will vary according to the x. Means what? At free end, beam has deflected more. At fixed end, beam has not deflected. It is zero. Deflection is zero at the fixed end. But from free end to fixed end, this y is not constant. It is variable with respect to x. As x increases, it becomes more because we are measuring x from fixed end. When x is equal to 0, deflection is also equal to 0. Okay. So it is just a mathematical function. That is what we have written. Y is, or deflection is y of x. Okay. Next. Consider a small portion dl, which we have already marked. Consider a small portion dl deflected curve at a distance of x from fixed end. At a distance of x from fixed end. Radius of curvature is r, capital R. Radius of curvature is r, and deflection curve makes an included angle d theta at the center of curvature. Makes an included angle d theta at the center of curvature. What you can do is you can do those modifications for that small portion there itself, or you just draw enlarged image. So what I will do is I will draw enlarged image, that is this portion. That is what I have considered. Okay. From this, what I will do, I will draw one tangent. then this as O, and then this as d theta, and this will be my radius of curvature. Similarly, drawing these 2 points. This is like nothing but the arc, similar to that arc. This is the contact point. This will be my dy, and this will be dx. Okay. So this whatever deflection curve is there, that I have just tried to simulate on this tangent. Okay. So this is what we have done, and I can call this is my x-axis, this will be my y-axis, and this angle is nothing but the theta or slope, you can call. This angle is nothing but the slope. Okay. So r d theta, dx and dy. This is dx, this is dy, and that will be your d theta. Okay. And that curve is nothing but the small portion, whatever it is there, that is nothing but the dl. That is curve portion. So dl. So if I apply Pythagoras theorem here, dx square plus dy square is equal to dl square. Okay, that is what we need to write. Okay, write down. From figure, again now I will be writing with respect to this figure. From figure, length of the arc, that is dl. From this figure, length of the arc dl is equal to r into d theta. R into d theta. Similarly, dl is also equal to under root dx square plus dy square. Dx square plus dy square. See here, I have taken r into d theta. Those are the projections I have taken. This is nothing but the dx or dl. This is dx and this is dy. From Pythagoras theorem, I can write directly dl is equal to dx square plus dy square. So dl is equal to, if I take dx common, under root 1 plus dy by dx the whole square. I have taken dx common, so dl is equal to dx under root 1 plus dy by dx square. Next, slope of the curve at a distance of x. Slope of the curve at a distance of x. See, x is the distance which is measured from the fixed end at a distance of x. So what is slope? Slope is nothing but the theta. So tan theta is equal to, this is theta. So tan theta is dy by dx. Tan theta is equal to dy by dx. Okay. And what I want? I want slope. Slope is nothing but the theta. Therefore, theta is equal to tan inverse of dy by dx. You can call this, whatever tan theta equation, you can call this as equation number 1, and slope theta is equal to tan inverse of dy by dx. Next, differentiating equation number 1 with respect to x. differentiating equation number 1, this is equation number 1. Differentiating equation number 1 with respect to x. So differentiate. What is differentiation of tan theta? Sec square theta. So sec square theta d theta by dx is equal to, what is differentiation of dy by dx? Is nothing but the d square y divided by dx square. Sec square theta d theta by dx is equal to d square y by dx square. Now just simplify this. Get me answer of d theta. D theta is equal to 1 divided by sec square theta, okay, into into d square y by dx square into dx. This dx will also go that side. So this is d square y by dx square. So d theta is equal to 1 divided by sec square theta. This will come this side, d square y by dx square into dx. Okay. Call this as equation number 2. Call this as equation number 2. Next. We know that, what do we know? We know that from trigonometric functions, sec square theta is equal to 1 plus tan square theta, because this is one trigonometric relationship that which is already known to us. Sec square theta is equal to 1 plus tan square theta. So substitute, what is tan theta? Is dy by dx. So tan square theta will be sec square theta is equal to 1 plus dy by dx the square. So sec square theta is 1 plus dy by dx the square. Substituting, we want that sec square theta value there in equation 2. So write down. Substituting sec square theta in equation 2. Substitute in equation 2. So substituting this value in equation number 2. So what will you get? D theta is equal to 1 divided by sec square theta. Therefore 1 divided by 1 plus d square y, okay, by dx square multiplied by d square y by dx square one divided by, okay, 1 plus d square y by dy by dx square into d square y by dx square into dx. That is what we have substituted. Also, what do we know about d theta? We have done somewhere d theta here. Okay. So d theta is equal to dl by r. Same can be substituted here. Substituting value of d theta in this equation, what will you get? dl by r is equal to 1 divided by 1 plus dy by dx square into d square y by dx square into dx. That is what you will get. Already we know value of d theta. Same again we will be substituting dl by r. So send that dl that side. What you will get? 1 by r is equal to d square y by dx square, d square y by dx square into 1 divided by 1 plus dy by dx square into dx, and that 1 by dl by r, that dl will come here. Okay, this dl will go and sit here, that is dx divided by dl. Now what you have for dl? dl is this. dl is equal to dx into under root 1 plus dy by dx square. Substitute that. 1 by r is equal to d square y by dx square multiplied by 1 divided by 1 plus dy by dx square into dx divided by dl. dl is dx under root 1 plus dy by dx square, 1 plus dy by dx square. Okay, this is, now you can see here 1 plus dy by dx square is there, and 1 plus dy by dx, it is under root square is there. So this is what we can say, it is like simple. Okay, here it is under root, so these two things can be clubbed together. So altogether it will become raised to 3 by 2. Okay, it is one root and it is one complete. So if I add that, it will become raised to 3 by 2. So I'll just simplify that. 1 by r is equal to d square y by dx square. Okay, d square y by dx square into 1 divided by 1 plus something has gone, d square y by dx. Right, this will go, because multiplication. So 1 plus, right, dy by dx, it is square raised to 3 by 2. Right, 1 plus dx, 1 plus dy by dx raised to 3 by 2. Altogether it is 1 plus dy by dx, and here also 1 by dy by dx, it is raised to 3 by 2. So write down. For small deflections, okay, for small deflections, slope, that is dy by dx, is small. For small deflections, slope, that is dy by dx, is small. Hence, dy by dx square, because here we are having square, slope dy by dx square is very small. And again, its third root by 2 we need to take. So again that quantity will be, we assume it as a negligible quantity. Okay, so above equation, what we have written, for small deflections, this dy by dx is very small, hence dy by dx square is also very small. Therefore above equation, that is this, can be modified as 1 by r is equal to d square y divided by dx square. Above equation can be modified as 1 by r is equal to d square y divided by dx square. Okay, this is one part. That is radius of curvature and d square y by dx square. Now, next, we have done the bending equation. From that, we'll take one more reference. Also, we know that sigma by y is equal to m by I is equal to E by R. So suppose here deflection is a curve which will be associated with the bending. So bending which will happen due to bending movement. Okay. So this I will consider. Also sigma by y is equal to m by I is equal to E by R. Therefore, what will we get here? From this 1 by R is equal to m divided by E into I. M divided by E into I. You can call this as equation A and you can call this as equation B. Equating equation A and B. Equating equations A and B. We get, I'll write here, equating equations A and B. We get, what do you get? 1 by R is a common. Therefore, m divided by E into I is equal to d square y divided by dx square, or m is equal to EI into d square y divided by dx square. This is what do we call is deflection equation. M is equal to EI into d square y divided by dx square is your deflection equation. And whereas EI is flexural rigidity. Okay. So E and I is your flexural rigidity. EI is flexural rigidity. Continue. The above equation is governing differential equation of second order, governing differential equation of second order for deflected curve. For deflected curve. It is also known as moment curvature relationship. It is also known as moment curvature relationship. Okay. So quickly I will tell what all things we have done. See, first what you have to do is you have to take one cantilever beam which will be subjected to the point load as shown. Initially the condition of beam is like this. When we apply load, beam will deflect into some curve. On that deflected curve, I will take one small random portion and at a distance of x from the fixed end. Now this is enlarged here. What I will do, I will try to join those two ends. Where they meet, that point I call as an O. This is nothing but the radius of curvature. How that curve is going to be traced. That is nothing but the radius of curvature. Then I will project these 2 points. This is nothing but the length of the deflected curve. I will make proportionates, or due to projections, I will have one with respect to x-axis as dx, one with respect to y-axis as dy. And also this inclined one I will assume to be is equal to the dl. Okay, nearly I will assume to be equal to the dl. So I get two things. One is this length of the arc. Length of the arc is r into d theta. Similarly, with Pythagorean theorem, this is dx square plus dy square. From that, I will get some L dl by keeping dx outside, 1 plus dy by dx square. That is what do I get. Then later, I will get the slope. What is slope? Slope is nothing but the theta. But from some relationships, mathematical relationships, we get tan theta is opposite upon base. So dy by dx. So what is theta? Tan inverse of dy by dx. Then tan theta is equal to dy by dx, that I will differentiate with respect to x. What is differentiation of tan theta? It is x square theta. D theta by dx is equal to d square y by dx. That is what is shown here. Then I will equate for d theta. I will send this term this side. I will call that equation number 2. Now next thing what I want is, I want this x square theta value. So I know from trigonometric relation, x square theta is 1 plus tan square theta. I know tan theta, it is dy by dx. I will substitute here, 1 plus dy by dx whole square. This value I will substitute here. What I will get? D theta is equal to 1 divided by 1 plus dy by dx square, and remaining terms as it is. Then d theta also we have found out from, it is r into d theta is dl. But then what is d theta? That is nothing but the dl by r. So dl by r I will get here is equal to as it is. Then 1 by r I want, dl I will send this side, which is shown here. Okay. Then here dy by dx square, 1 plus dy by dx, these things, okay. So dx and dx will get cancelled. Okay. And dl, okay, from previously we'll get dl is equal to under root dx square plus dy square. So that dl I will substitute here. Once I substitute that dl, these things will get cancelled. So this dx and this dx will go, then this will remain. Now this is one entire term, this is one under root. I will add those two because it is simply, it is like this. See here. How do we write 2? 2 is root 2 multiplied by root 2. It is on the same lines. So this is one you can call 2, and there is one which is root 2. Okay. This is complete number. This is half that. So 3 divided by 2. Together I can write. Okay. 2 raised to 3 by 2. That is what I can directly write. That is what I have written here. Then for small load or for small deflections, slope is 0 or slope is small we can call. See here. Here deflection is very small. Slope will also be very small. Like that, when I go with a larger value, larger. But I will assume that it is like slope is small. And when you do square of a smaller quantities, again they become very smaller. That's why I will neglect that entire term. So I will arrive at one simplified relationship, that is 1 by r is equal to d square y by dx square. I will call this equation A. Similarly, bending equation we have done. That is sigma by y is equal to E by r is equal to m by I. Here I am relating with respect to the m by I and E by r. So from that I will equate 1 by r is equal to mi, that is okay, m divided by ei, that is nothing but the 1 by r. I will equate both. I will get by deflection equation m is equal to ei into d square y by dx square, where this product is called as flexural rigidity. Sometimes you need to calculate, or E will be given, I you need to calculate, or sometimes in numerical this value will be directly given to you as a flexural rigidity. This is deflection equation, the most important thing from second half of this unit. Okay, this also can be asked. That is, first part is bending thing, where we have seen the derivation of a bending that we have derived. Reference had come here at the last. Okay, we have seen the problems with respect to the bending stresses, also with respect to the shear stresses. One sample problem we have seen with respect to the shear stresses. Now, this is what we have derived is nothing but the bending equation. Okay, sorry, deflection equation. Now, in your syllabus, it is clearly mentioned that we need to check simply supported beam and cantilever beam subjected to point load only. So by double integration method, one case will solve. That is cantilever beam subjected to point load. There is one more case which is there in all textbooks. Simply supported beam subjected to point load at the center. That you have to do it similar way to what we are going to do it now. So there are two cases. Now take down first case, write down cantilever subjected to point load. Only introduction will take. Tomorrow we'll do that. Then we'll do some problems onto this. Okay, write down. Cantilever beam subjected to point load. Cantilever beam subjected to point load. That is case 1. You need to remember this equation. M is equal to EI into d square y by dx square. I'll write that what we have got, M is equal to EI d square y divided by dx square. You need to remember this. Okay. So case 1. Case 1. Cantilever beam point load, subjected to point load at its free end. Write down. Consider a cantilever beam with its free end subjected to W, subjected to point load W, subjected to point load W as shown below. As shown below. Take a section XX. Take a section XX at a distance of small x, at a distance of small x from free end, at a distance of small x from free end. Okay, I will draw that. First, cantilever means it should come to your mind. One end is fixed, other end is free. It is subjected to point load W. I'll call this fixed end point as A point. This is B point. It is subjected to load W. Earlier we had inverted load, so beam has bent into sagging. Now load is acting from the top at the free end, so beam will bend in a hogging. Okay. Now next, any random section you need to take, like in SFD, BMD, how we have done. So XX at a distance of small x. That is what? It is a cantilever beam. I will name this as point A. I will name this as point B. Take any random section XX at a distance of small x from free end. It is subjected to W. Okay. So today we'll stop here. Tomorrow we'll continue this case study. Again, I am telling there are two case studies. One, you have to do it by yourself. Supported beam subjected to point load. That is sorry. We'll continue this tomorrow. Then we'll take numerical.
and we'll see what is Macaulay method also. Okay.